Good afternoon, everyone. Thank you very much for being here. My name is Andrea Cavalli. I'm honored to chair this first mixed-gen session, which is season number 3 and session number 3. I'm the new director of SICAM, and starting from January 1st, 2023, and I'm delighted to be here and to share with you this session related to soft matter and machine learning. Following the standard mixed-gen format, we have 3 speakers, one senior researcher, and 2 younger investigators. The senior researcher is Laura Filion from Utrecht University. And then we have 2 postdocs, Alessandro Coretti, working in the group of Christophe Del Lago, University of Vienna, and Atreyer Banerjee, working in the group of Kurt Kremer at the Max Planck Institute for Polymer Research in Germany. And without any further delay, I would like to start this scientific discussion with the speakers and with the attendees, and also during the poster session. So I leave the stage to our first speaker, Laura Filion from the University of Utrecht. The title of her presentation is Soft Matter and Machine Learning. Please, Laura, the stage is yours.
Can I just check that my screen is shared properly? Can you see it?
Yes, it is. Yes, it is.
Okay. And I'm changing the pointer. All right. I hope everybody can see my talk now. And I would first like to thank the organizers for organizing, I think, what is going to be hopefully a very interesting session. I'm very much interested to hear what everyone is thinking. And it's my pleasure to actually start the session off with a talk. And what I do want to talk to you guys about today is soft matter meets machine learning, or at least applications of soft matter and machine learning. But of course, soft matter and machine learning, as we're going to see at the beginning of this talk, is really, really broad. So let's go with a little bit of a focus for most of the talk, which is not just soft matter meets machine learning, but really with a focus on how we can use various kinds of machine learning methods to understand structure, and in particular also the interaction between structure and dynamics in disordered systems. And so we're going to walk through a number of different aspects in the next a little under an hour. And so for anyone who doesn't really know what's going on here at all, what is soft matter? What are these words in the title? So soft matter, if you like, is kind of generally a group of systems which have the feature that they can be structurally changed by thermal or mechanical stress, whose magnitude is on the order of thermal fluctuations. So that's a fancy way of saying, in my mind, that if you're looking at the interactions between the building blocks in these systems, or the interaction scale that matters, then it's on the order of KT, which implies that entropy is usually very important in these systems. They have yield stresses, they're deformable. Building blocks are generally large compared to compared to atomic scale, which means that generally you can use classical physics to capture the behavior. And it includes things like colloids, liquid crystals, emulsions, polymers, these kinds of systems. And actually my expertise in soft matter is much more focused actually most of the time on colloidal systems. And that will also be a little bit connected to the kinds of systems I'm talking about today. And so what is a colloid? So a colloid is a particle which is trapped somewhere between a nanometer and a micrometer in size, and which is suspended in a solvent. And the important part about this is that as a result of being small and in a solvent, they're actually undergoing Brownian motion. And so if you look at these particles, they're bouncing around, and this allows them to explore their phase space and self-assemble into different kinds of phases, the same as you would get on the atomic scale by atoms. And so they can, if you look at the colloids themselves, they can appear to be in crystal phases or liquid phases or gas phases. And we can also see behavior such as glasses in there. In addition to, in the title, in addition to soft matter, we also had this term machine learning. And I think a lot of us, I think today have a picture in our head about what we mean by machine learning. Mine is relatively simple. So if you just go to machine learning, go to Wikipedia and you ask, well, what is machine learning? It would say that it's the field of computer science that gives computer systems the ability to learn with data without explicitly being programmed. And to be honest, in my view, or the way I see it, machine learning is really just modern data analysis. It's a very fancy and can be very, very developed versions of modern data analysis, but it's really a modern way of dealing with data. And so this is going to be at the heart of a lot of the topics that I talk about today. And there are many, many different kinds of machine learning algorithms out there. And they can generally, not always, be categorized into two separate categories. You have what's called supervised machine learning, which is really just a fancy way of fitting a function or classifying data. You have some function, you have some box that you're going to try to learn. You have input, you want to get a desired output, and you try to learn a function that gives you specific output from your input. It's a fancy version of fitting, if you like. And you have also unsupervised algorithms, and unsupervised algorithms attempt to extract the most important data features that characterize the variation in data sets. And that's a bit of a fancy way of saying, okay, I have a big data set and I would like to say, okay, what are the largest differences in the system that an algorithm can find? And can I then, with human intelligence afterwards, give these large structural variations or give these large variations in my data some meaning? And we're actually going to see examples in the talk today of both supervised and unsupervised machine learning. So I just wanted to get this terminology out there from the very beginning. And so, as I said at the beginning, there's actually many, many applications you could dream of applications of machine learning in soft matter. You could ask, and actually I think a very nice one recently, if you're a computer simulator, is coarse graining. So we can use machine learning algorithms to coarse grain interactions in soft matter systems. We can use machine learning to try to identify phase transitions. We can use machine learning to try to take a pile of data that connects structure and properties of materials to each other, and then try to learn the relationship between structure and properties. I think a nice application is even things like reverse engineering. We say, okay, I would like to get a specific crystal structure. I would like my materials to do a very specific thing. Can I engineer particles that would do that? And there's answers in machine learning, or at least there are methodologies you could apply from machine learning in order to try to address these questions. And of course, the one that I want to talk about today is really how can we use machine learning to get information about structure and dynamics in our systems. And so I'm going to, while there's this really big, vast amount of information you could imagine applying machine learning to, I'm going to zoom in on a very specific topic, machine learning and its connection to structure and dynamics. And even there, that can be very broad. So I'm going to just cherry pick things that I've worked on in the last couple of years. So let's start off with kind of the simplest question you could imagine in a structural case, which is, what is the local structure of my particles? And to be honest, whether you do simulations or you do experiments, if you have objects or if you have some kind of building blocks, one of the questions you're very often going to ask yourself is, in what structure have my particles organized themselves? Or while some process is happening, you might be trying to understand that structure. And so if you look at this picture that I showed you here, one of the questions you might ask are, is everything disordered, or are there any crystalline parts? And your eyes are really great at going, okay, actually, I see some little bit of order in that system. And actually what we're seeing is kind of a coexistence of a fluid and a crystal, and it's actually because there's a little bit of a crystal nucleating in a fluid at the moment. And one would like to have autonomous ways of an algorithm going in and answering this question: which particles should I color blue? Which particles should I color red? Why? And so this is an important question if you want to study structure in your systems. And again, regardless of where these came from, simulations, experiments, etc. And so there's really three directions that you could go to answering this question. You could imagine human designing algorithms, and we'll talk about that in a second. And that's how we did it for most of my career. So you go in and you say, okay, I have this structure that I would like to be able to pick out, and I'm going to dream up a way of doing that. And that's a very nice way of doing it in a sense. And we've done that a lot in the past. But as we're going to see, there's situations in which that might not be the most appropriate way to go about it. And you might want to develop either supervised machine learning algorithms or even unsupervised machine learning algorithms that allow you to address this question of which particles are which in the system that I'm looking at. And so let's start off with kind of the most oldest of the three methodologies, which is human design. And so in this context, what is the goal? The goal is to develop an algorithm that can distinguish, really, when I look at a single particle in this system, what kind of environment it's in. And so is that single particle more fluid, more crystalline? And if it's more crystalline, can I even tell you which type of crystal? Is it more in a face-centered cubic environment, more in a hexagonal close-packed environment? So what environment is a single particle in if I look at its neighborhood? And there's, of course, a number of different ways you could imagine going about doing that. Sorry, the slide went automatically, accidentally. And one of the ones that I'm going to, well, the one I'm going to talk about today is bond order parameters, but that's not the only way. There's all sorts of people who've asked this question in the past, and there's been developments of templating methods, there's common neighbor analysis, and there's other kinds of algorithms you could imagine for identifying local environments, but we're going to focus today on bond order parameters. So what is a bond order parameter? Well, to me, it's kind of the first thing you would do as a physicist looking at an environment that has the potential of order, and you want to be able to pick out that order in some way. And so what the idea is, you take a number of particles in the vicinity of a particle, maybe via the first peak in the radial distribution function, you define those as neighbors of your particle, and then you look at their structure by expanding the density around the particle in terms of spherical harmonics, and using the density expansion to create rotationally invariant quantities. And so kind of more mathematically, what do? I take my particle, I identify its nearest neighbors, I expand the density around it in terms of spherical harmonics, which is this first equation, and then I generate rotationally invariant quantities from that, which is then the second equation that I give you here. And then it turns out, it was shown by Lepner and Delago, that actually it works even better if you average over the neighborhood, if you're trying to identify different crystal structures from each other. And so then in principle, if I look at this, and even if you look at this parameter here, what we actually are constructing is bond order parameters for a specific L. So for a specific type of symmetry. L equals 2, 3, 4, 5, 6. In principle, you could have a whole variety of them. And the human intelligence part, if you like, that's going to come in is which Q might actually give me some information about the structures I'm interested in. So let's start off the question by one of the simplest cases I can imagine, which are just hard sphere crystals, or hard sphere, a system of hard spheres, so marbles. And these can form a number of different phases, or there's a number of different phases you could imagine seeing in these systems. And so we could ask, okay, well, how can I actually distinguish them if the only thing I have at my hands are bond order parameters? And it turns out that if you choose two of these bond order parameters, Q4 and Q6, then it's actually possible to reasonably well distinguish particles which are in a local liquid environment from particles which are in a local body-centered cubic environment, from ones that are in a face-centered cubic to hexagonal close-packed. And so all of these different structures that we expect to see we might see in hard sphere systems, we can actually distinguish based on just this two-dimensional plot of Q4 and Q6. And since we'll see other plots like this later today, let's just be very careful of what we're looking at. These are a pile of simulations that were run in the phase, so in body-centered cubic or FCC. And then each dot you see is a single particle from that system, from that bulk system that was either FCC or BCC or HCP. And so then each one, because of thermal fluctuations, is in a slightly different environment. And so you get a cloud of points associated with each particle in this environment, and we can find all four different ones just easily. But actually, if I think about colloidal particles, the chemists are really amazing, and we don't only have spheres to play with, we actually have a variety of different systems to play with. We can imagine particles of different sizes, particles of different shapes. We can also look at mixtures of different particles together. And if what I'm doing is manually every time determining, okay, how can I distinguish based on, this order parameter, all of these different phases, it can be actually a very difficult challenge, and it might not even be possible always. And so the question that we have is, instead of doing this kind of trial by error where I figure out that I want to look at Q4, Q6, we ask ourselves, is there a better choice via machine learning? And of course, I wouldn't be asking this question if I didn't think that the answer was yes. And so one of the easiest ways that's kind of directly associated with what we just did is we say, okay, we're actually going to just train a machine learning algorithm to recognize specific crystal structures. And so we can do that using something like a neural network, where instead of taking only Q4 and Q6 to represent a specific particle, we take Q2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, however many you want, to collect local structural information about your particle. And then you, again, if you're a simulator, you make simulations of each of the different phases you're potentially interested in, and you fit a function to recognize that this set of Qs actually corresponds to FCC, another set of Qs corresponds to BCC. And so it's able to actually learn the relationship between this local structural description in terms of bond order parameters and the identity of different crystals. Of course, one of the assumptions that we're making here is that we have such a body of data, that we have a collection of snapshots in BCC, we have a snapshot of collections in FCC, or whatever other phases we're interested in, so we can use those to train the algorithm. But if we have that, and if we can generate them, we can create an algorithm which can distinguish different local environments. And actually, together with a master's student and then a PhD student, so Michel Rand and Emanuele Boettini, we applied this to all of the different structures that are formed in binary hard sphere mixtures. And we were actually able to, with very high accuracy, train an algorithm that could recognize different structures. And here's just a specific example. So if you take binary hard spheres, so hard spheres which have then two sizes, and the size ratio of the diameters are 0.58 in this case, then it turns out that we know from literature it forms face-centered cubic lattices of both species, and it forms two kind of funny crystal structures, one called aluminum diboride and one which is an AB13 structure. And actually it can recognize all of these different phases as well as a fluid phase to a very high degree of accuracy. And so this is a very nice solution when I'm able to do simulations. So I need to have a way of generating all of these configurations to learn from. And when I know what phases, I might even be interested in STEAing. But actually, there's an interesting other question which you might ask is, what happens if I don't know what I'm actually looking for? So what happens if I don't even know what structural features I'm trying to set out to look at? And so that's another nice question we can try to address with a different type of machine learning. And now instead of supervised, where we're doing some kind of classification, we're going to use unsupervised machine learning and just ask it, okay, I'm giving you an image. What is the largest structural variations you can see in the different particles in my system? And I think one of the first papers that came out on this, which was a very nice paper, was in 2017, where they did machine learning for autonomous crystal structure identification. This algorithm turned out to be very slow and kind of complicated. And actually, they made a very nice improvement on this in 2018. But we're also going to look at this from just a slightly different picture and see if we can ask this question in a very easy way. So the goal we had whenever we started out with this project was to develop a simple and fast algorithm that was able to autonomously identify different distinct local environments without any knowledge a priori of what we were actually looking for. And we wanted it to be very robust. And actually, at the end of the day, we're going to even talk about glassy systems. So looking for disorder in disorder, different kinds of disorder in disorder. So we wanted a very robust algorithm. And we thought that there would be three key points. So, I just wanted to point out there's a lot of other people who've been looking at this question over the last few years. So here's just a selection of some of the different literature you might find interesting on the topic. But okay, to design such an algorithm, we thought there were three key points that would be interesting. One, which is, or essential, if you like, one, which is a description of the local environment. If I take a particle, I want to know what is the area, what does the vicinity of the particle look like? So I need a way of describing that. And in principle, I started off with the question, okay, I wanted something that could distinguish liquid and crystalline environments and different crystalline environments. So symmetries were very important for us whenever we started asking these questions. We also want a way of lowering the dimension. So I want to have a very complex description of this environment, but I want to have some way of interpreting that very complex description by lowering the dimensionality, and as a result, looking at different structural features in this system, and then finally grouping together environments that are somehow similar. And so we're going to see quickly how we can do that. So as far as a description of the local environment, we're not going to do anything new at all. We're actually going to do exactly what we did before, which is just use bond order parameters. So I'm not going to introduce anything new. We already have a way of describing the local environment, which is bond order parameters. We're going to use it again. And so then the next question is, how can we understand and distinguish the local environments in the system? And so just as a starting point in your head, so what are we going to be trying to accomplish here? Here's an example snapshot, and actually I know what's in it because I made it. It has a mixture of a fluid phase on the left and the right-hand side. It's a periodic box and there's a fluid. And then sandwiched between this fluid is actually a chunk of face-centered cubic and a hexagonal closed packed crystals. And so we're going to describe the environment of each of those particles using a bond order parameter, like I said, so that allows us to describe the particles. And then the next question is, how do we go from this large description of each of the particles in that system to something I can actually start looking at and trying to understand the data for? What we did in human learning was actually just, okay, say I only want 2 of them. We're not going to say I only want 2 of them. I'm going to ask, okay, is there a way of compressing this information in a way where I can see the largest structural variation? And we did that with something called an autoencoder. This is a way of dimensionally reducing your system, which allows for a nonlinear dimensionality reduction. And so it's actually very simple, even though it might sound complicated. So the goal of an autoencoder at the end of the day is going to be lower the dimension of the system. But as a first step, it does actually what feels like almost nothing. We're going to take input. This is this whole big set of cues, and I want to put in my big set of cues for every single particle. So take a single particle, express it in these cues, and I want to get output, which is actually the same cues. So I would like a neural network that I dump in the middle that does absolutely nothing, that learns the identity matrix, which is kind of a boring thing to try to do. You say there's many ways of doing that. But the neural network is going to be designed in an intelligent way, which forces the information through what we call a bottleneck, through a lower dimension. And so the idea is that if I can take my input and I do a good job of reproducing my output, but I push it through something of lower dimension in the process, then actually that means that I've captured the relevant information in this lower dimension. And so what we actually do, we can see on the next slide. Oh, and then after we've done that and after we've trained this, we just take the first part, which lowers the dimensionality, and we can use that to lower the dimensionality of our system. So what does that look like in a little bit more detail? So we do basically the following. We take each single particle in this system, we expand the environment in terms of a vector of these bond order parameters, and then we send in the particle's environment, we try to reproduce it on the outside, and we learn in between with some kind of network a relationship that takes us from as close to the identity as we can. And we push it through a bottleneck. And so we put all of the particles through this loop, and we try to learn this or learn this lower dimension. And then at the end of the day, we grab the front part and we project all of the particles again down onto this lower dimension. And so if I take this coexistence system that you just saw a second ago, and I put each particle through this algorithm after it's been trained, I actually get the following. I push it through to 2 dimensions. So I have just 2 directors here, and I see each dot represents a particle, and we see 3 different clouds of particles very quickly. And actually these 3 different clouds of particles are telling me, even by eye immediately, that I've got 3 different environments my particles can kind of be grouped into. As a point of interest, this is very fast to do. It was done on the single snapshot that you could see, and it takes minutes on a laptop. So it's really something that happens very, very rapidly. One of the questions you could ask is how low dimension can I get? And so that you most of the time do by trial and error. You try a couple of different lower dimensionalities, and since it only takes a few, well, maximum a minute or so to do, you can check to see, okay, how much information can I get if I go to 2 dimensions, 3 dimensions, 4 dimensions? And so you can actually explore the dimensionality that you need. There's also some tricks for choosing the best dimensionality, but most of the time we do it by exploring what happens, because it gives us a bit of a better feel for the system. So what have we done? We've described the local environments. We tried to understand the distinguishing features in it. And now we want to group together different environments. So clustering, and there's many different ways you could use. We used Gaussian mixture models where you basically just fit this density profile to different Gaussians. And so as your eyes would actually say, there seems to be 3 local environments in the system. We get 3 different Gaussians. And then actually the only thing that the unsupervised algorithm tells you is that these are 3 different things. You still have to, as a human, go in and say, what distinguishes these 3 local environments? And what you find whenever you look at them is that one of them corresponded to fluid, 1 FCC, and 1 HCP. And then we can go back and color our image according to this classification, and we find that indeed there's fluid particles, there's particles that are red and blue, and these turn out to be corresponding to, well, the purplish ones are HCP in like environments, and the bluish ones are face-centered cubic-like environments. And if you're interested in this, the paper is here on the bottom. And actually, of course, the hard sphere case is something that's been solved a long time ago. One of the questions we could ask is, of course, how robust is this algorithm? Can I apply it to problems where I don't even have an order parameter? And so we went and dug through our samples just to see if we could find other situations which might be interesting to look at. And just as 3 examples, here I show you grain boundary situations, anisotropic particles, and even nucleation in a binary system. And in all cases, this simple algorithm, which takes a single snapshot, gave us different environments which corresponded to what we expected. So we are able to pick out grain boundaries, we're able to pick out fluid and crystals in anisotropic particles, and we're also even able to pick out crystals which are nucleating from a binary environment. And so this was actually kind of success from our perspective, and I think it's a very nice example of what you can do with unsupervised machine learning. But we decided to push the algorithm even further and ask, instead of can it distinguish different crystalline environments from a fluid, or even crystalline environments from each other, which are all symmetrically quite different from each other, can we go even further and ask it to distinguish disorder from disorder? And so if we take a system which is disordered, can it identify different kinds of disorder? And a classic place where that question might be very important is in supercooled liquids. And so if you look at a liquid as it's kind of approaching a glass, we know that the dynamics become very heterogeneous, and we expect that there's different structural features connected to these dynamic heterogeneities. And the question we're asking is, if we ask the algorithm in a liquid, what are the largest structural variations? Is it going to turn out that the largest structural variations are somehow connected to dynamical variations? So we're asking, can we find a structural order parameter, if you like, in this disordered system of a supercooled liquid? And so to do this, we actually looked at 3 different glass formers, or glassy systems, which are all basically very similar in a sense. They're all just binary mixtures. One was binary hard spheres, which we've already talked about today. One which are just binary repulsive particles, so binary WCA particles. So they're very similar to hard spheres, but now instead of being purely hard, they push a little bit away from each other using just the repulsive part of the Leonard-Jones potential. And then also a binary mixture, which has been looked at a lot in the context of glassy systems, which is called Cobb-Anderson mixture, which is just non-additive binary mixture of Leonard-Jones particles. And so all of these we already know a fair bit about, and I'm just mentioning them so that we can see results from them. But they're binary mixtures which are relatively supercooled, which means that we expect dynamic heterogeneities, and we're going to ask, what do we see in the structure of these systems? And so we fed all of these algorithms, all of these different systems into our unsupervised machine learning algorithm. And in all cases, it said that, basically we could find 2 clusters or 2 different local environments, largely. And then we were able to kind of develop a single scale, because there were only 2, we could develop a scalar order parameter, which said whether we were likely to be in one or the other. And so a scalar order parameter, which I'm going to call P red from now on, just says, what is the probability that my particle is in one of these 2 environments? And so we can then color particles in our system according to their P red, so according to whether or not they were in one of the specific clusters. And so we take a snapshot from our hard spheres, we take a snapshot from the repulsive spheres, and a snapshot from the Cobb-Anderson mixture. And we see that, okay, structurally, this algorithm says, okay, there seems to be different structural regions in the system. The red particles are more one structure, the white particles are more another structure. But one of the questions one might have at the end of this is, okay, but does this structure mean anything? Or is this just basically what the algorithm gave because you asked it to do something? And so then we had the question, do these structural variations correlate at all with dynamics that we see in the system? If we're going to do that, we have to ask, well, what kind of dynamics might we be talking about? So how can we capture the dynamics even to ask that question? And so to measure the dynamics in the system, we measure something called the dynamic propensity, which is a kind of a measure of the average dynamics a particle in a given environment might have. So you take a snapshot, a simulation of your system, you make 50 copies of exactly the same, or 100, it doesn't matter, but make multiple copies of exactly the same snapshot. You scatter the velocities in that system, and then you let your simulation run, and you see on average, from that specific configuration, how far on average do the particles move. And then you calculate them, you measure the absolute displacement of a particle over some specific time interval, and then you average it. And so particles move on average some distance at a specific time interval, and then you can, well, for instance, here we colored them darker if they moved more. But this is a measure of the dynamic propensity of kind of the likelihood of a particle to move a certain distance given its current initial environment. And of course, the dynamic propensity, you can then average the dynamic propensity over your entire system if you want to get a feeling for what it's saying and what you can recognize if you do that. So here we plot on the y-axis the dynamic distance traveled on average, and then on the x-axis the time, and you see 3 different regimes. And in these glassy systems, you see a ballistic regime where the particles haven't really found out about their environment yet. Then you see a caging regime where the particles are kind of stuck locally, so they don't make much progress over that time scale. And then you see the diffusive regime, which is the last time scale on this. So we have ballistic, caging, and diffusive, which are easily recognizable if you average the dynamic propensity over your entire system. But of course, you can look at it on a single particle level and ask, how much does the dynamic propensity connect to the structure? And so we did that as well. So you take all of the structural order parameter, you plot it at the top, and then you have the dynamic propensity, which is plotted per particle on the bottom. We took the snapshots or the time interval for which we had the biggest agreement, which is somewhere in the vicinity of the structural relaxation time of that liquid, of that supercooled liquid. And you actually see by eye, at least, there are some correlations. I mean, if I look at this hard sphere system, I see that the red particles here seem to correspond to the red particles here. And by the way, the colors are just me choosing, right? So I've chosen that the red particles will be colored red to make life a little bit easier. But the variation here, which is red to white, seems to go with the variation here. And that's very important. And so it's saying that the dynamic propensity, the differences correspond very strongly to the structural order parameter. But this is just by eye, which is not a good way of correlating things. Of course, we can actually calculate a correlation function. So for instance, a Spearman correlation function, and see how much correlation do we have at different times. And so in all of these plots, and there's going to be a pile of them, I think, in the next little while. So let's talk about them. On the y-axis, we have the correlation between the predicted dynamic propensity, between the structure and the dynamic propensity, the measured dynamic propensity. And then on the x-axis, we have the time. So at different time intervals, you get different dynamic propensities, and so hence you can look at it at different times. And what we see is that around the structural relaxation time, which is what I'm calling tau alpha, so the times in this have all been scaled according to the structural relaxation time of the supercooled liquid. What you see is actually a correlation somewhere 0.6, 0.7 for hard spheres. It goes down a little bit for the WCA. So for the repulsive particles, it's around a little below 0.6. And actually this Cobb-Anderson mixture, it goes down actually significantly to a little bit, to something like 0.4. So it doesn't do nearly as well, but we still do see a reasonable correlation between the structural variation in the system and the dynamics in the system, which is an interesting observation. And something I wasn't expecting necessarily at the beginning. One can also then ask a little bit more, do we kind of believe that these structural regions or the structural variation that we're observing really means something? And one of the ways you might ask that question is, what happens as a function of temperature dependence to this order parameter? So if I'm looking at the particles which seem to be part of the red cluster, are there always just about the same number of particles in the red cluster, or is it changing? And what we actually see is that the particles which are part of the red cluster, which are on average the faster particles, because it was the red that was corresponding best with the dynamic propensity, we actually see that in the case of hard spheres and repulsive WCA and Cobb-Anderson, that as we supercool the liquid, the number of fast particles is actually going down. And so this actually, to me, indicates that at least the structural order parameter that we've developed in this unsupervised algorithm is saying something about the structures that are related to the dynamics in the system. And so our goal, I think we succeeded with rather dramatically. We have a very simple algorithm. It takes minutes to run on your computer. It's very easy to implement, and it actually can tell you a lot about variations in structure in a variety of systems. So just as a kind of mini conclusion from this part of the talk, we've developed an algorithm that's robust, it's simple, easy, fast, and the correlations actually work even very well in the glass. Well, let's say the structural order that it finds even seems to say something about the dynamics in a glassy system, which I think is very interesting. I would like to point out that this work that we did was actually in a very different way done very similarly to the group of Daniela Koslovic, at least all of the glassy stuff I just showed you. So actually on similar models, and actually sometimes exactly the same model, very, very similar things with an unsupervised algorithm were shown both in 2020, also by the group of Daniela Koslovic. So It's a different kind of unsupervised machine learning algorithm, but it also worked. So actually, in that sense, the results are very robust. So now for the last part of the talk, I want to flip the question a little bit. And instead of asking, can we develop algorithms that are able to distinguish local structure and then does that structure connect to the dynamics? Let's ask, can we fit dynamics with structure? And that might actually be very interesting in trying to understand problems associated with supercooled liquids. And so the question is really different. Instead of asking, what are the largest structural variations? And do they happen to correspond with glass to dynamics, which is a very unsupervised question. We're going to ask a very supervised question now, which is, can we develop an algorithm that's just able to take in the structure and give me, for instance, what I expect the dynamic propensity to be? And so in a kind of cartoonish picture here, I'm going to look at the structure around the particle, and I want to create a function that looks at the structure around the particle and predicts at some time later how much the particle will have on average moved, the dynamic propensity at that specific time. And this question actually was addressed by multiple people. I think not specifically the same question, but the group of Andrea Liu really brought about this in kind of the context of support vector machines, which I'm not going to go into in 2016. But then in 2020, I think the group of Victor Babst, group from Google, actually really tried very hard at using what at that point in time were kind of modern machine learning methods to fit this function. And so they use something called a graph neural network, and I will explain in the next couple of slides what that is, in order to be able to fit the local structure to the dynamic propensity. And again, this is kind of almost the same plot as what we saw before. Now we have the correlation between the predicted dynamic propensity and the measured dynamic propensity at different time scales. And the group of Victor Babst actually showed for the Cobb-Anderson system that they were able to get correlations up to like 0.7 almost. And this is exactly the same system we were just looking at for the neural network, for the unsupervised algorithm. And there we had, this is the Cobb-Anderson, so that was the stuff that was on the far right column always of everything. And that we had said went up to about 0.4 correlation between the unsupervised algorithm and the dynamic propensity. So it means that they've actually, using the supervised algorithm, found structure or been able to identify how structure connects to the dynamics much better, if you like. And so a much stronger correlation, which is actually not so shocking because one wasn't even trying to do this. It just asked if it happened. And this one is really trying to create an algorithm that actually really maximizes this correlation. But okay, let's go back and ask, what is a graph neural network? What does it do? And can we even learn a little bit from this graph neural network? Well, why does a graph neural network allow us to predict this, the dynamic propensity so well? So if you like, what did graph neural networks get right in the ability to predict? By the way, this is what you would get with linear. So the support vector machine, this kind of algorithm was down here. So they made a rather significant improvement at that point. So in order to answer that question, one first has to ask the question, how actually do graph neural networks work in the first place? And bear with me, this is a little bit complicated. I will try to do a cartoonish version, so a short, incomplete introduction to graph neural networks. In some sense, they're quite intuitive, but it's kind of messy simultaneously. The first step is you take all my particles and I put all my particles at nodes in a graph and I draw edges, lines between the neighbors. So this is kind of a structural input. I encode the feature and I encode on each of the nodes and the edges some kind of features. So I take my particles, I turn my particles into a graph, which are nodes and edges, and then sitting at each node and at each edge, I can put information. And for instance, I might put the distance between two particles. Maybe I put the vector between the two particles. Maybe I put the type of particles at the nodes. But these are the kinds of information you can encode into that graph. So you encode your system into a graph of nodes and edges. And for instance, as I just mentioned, you could have particle type and vector between particles, etc., etc. And then step one is to assign each node a vector of information based on, for instance, bond length, local environment. I just said that, sorry, I'm repeating myself. Step two is to encode each node and edge into a new set of parameters using a neural network. So just on the edge, I put a little neural network that maps that information to actually a bigger vector. And I do the same thing at the edges. And then comes the part that really matters here. There's going to be updates for the nodes and the edges. And how exactly do these work? moving you guys around so I can see my slide better. So basically if I want to update the information at the nodes, then I take the information that's at that specific node. I look at all the edges that are connected to it. I put all the information from the edges that connected plus the nodes that are nearby, and I plug that onto an edge, and I put that into a network that then feeds back onto that edge itself. So I kind of take all of the information that's connected, I use a network to then connect it back and dump it back on the edge in question. So that's what's called an edge update. And I can do the same thing with nodes as an update. I take the node, I take the edges that connect to the node, I connect that with a neural network back to the node itself. And then that's new information on that node. So that's an update of the nodes, an update of the edges. And so once I've done that, in principle, I have new information at the edges and new information at the nodes where the values are different. And I can just repeat that procedure again. I can run an update on all the nodes and edges again, and I can rinse and repeat. So I have all of the information at the nodes gets updated, all the information at the edges get updated, and every time it's getting updated, information from further away is coming in, because this network that's dumping onto the node or dumping onto the edges is taking neighboring information, but after one step, neighboring information is also coming from further and further away. And basically at each step, information kind of in an average quantity is ending up at the nodes and edges recursively. So at the final end, the graph neural network looks at a node and it takes the information that's at that node and it connects that to with a neural network to the dynamic propensity. And then all of this mess of neural networks gets put into something which is the graph neural network, and you feed it in structural information, or you feed it in your configurations, and you learn the dynamic propensity. So you learn all of the values for all of these different neural networks to try to get, at the end of the day, the dynamic propensity out of that. You've probably heard me say, a number of neural networks. As we've been doing this, I really have said a number of neural networks that connect all of these things together, because you end up in this one by Bobst with 70,000 fit parameters that are going to be fit in order to connect the input structure, which is encoded in a graph, to the dynamic propensity. There's a monster, the guy that's actually being fit here. And so the question that we had, I get depressed if I see 70,000 fit parameters to some degree. So the question we had was, is it possible to incorporate kind of this averaging and the way that information is being carried into structural order parameters instead of doing it using the algorithm itself? So can we just kind of design more intelligent descriptors of our local environments that somehow carry the same kind of information as the graph neural network? And if we do that, can we avoid the 70,000 fit parameters and maybe fit it with a much simpler algorithm? So can we incorporate this kind of recursive way of pulling information from further and further away into simple order parameters? So let's see how we can do that. So step one is to describe the local environment of my particles. And to do that, we're actually just going to use standard radial and angular descriptors. So I have, at a certain distance, what is the density, if you like, and what is the order of, let's say, L equals 2, 3, 4, 5, 6, etc. So very similar to the bond order parameters we had before, but now at a certain distance. And so each certain distance corresponds to a new order parameter itself. And then we generate averages. And actually, this is very similar to, well, this is basically what Lepner and Delago had done. They said, okay, if we average once, we actually are able to distinguish crystals better. So the first step is actually to average this quantity, these descriptors, over their local environment, which is literally all this is doing. It's averaging over the local environment. It's averaging the descriptors over their neighbors. So that's what we're going to call first generation. But of course, if I average them the same as in the graph neural network, where I could apply the edge updates and the node updates over and over again, I can do the same thing here. But if I try to imagine the similarity here, what the same thing would mean here is just doing another level of averaging. So I can average the averages. And so we average the averages to get a second generation of descriptors. But if I can average the averages, I can average the averages, right? So I can continue doing that, and I can get an nth generation of descriptors. And of course, as we do that, we're pulling in information every time from further and further away. And so in the end, we end up with for the 0th generation, for just the local structure, we had 200 radial functions and 192 angular functions. So just parameters that describe the local environments. And then we end up with per generation also all of these descriptors after they've been averaged. So you end up with a full description of my system with 0th generation, 1st generation, 2nd generation, out as far as I like. And every time I add a new generation, I have to add another, well, the same number of radial and angular descriptors again. So it gets bigger every time I add another generation. And then we fit actually just using standard linear regression. So we're just going to fit this using a linear function, all of these different descriptors to the dynamic propensity. We can ask, how well does it work? So here again, what are we plotting? On the y-axis, we're plotting the correlation between the predicted propensity, dynamic propensity, and the actual measured dynamic propensity. And on the x-axis, we have the time. And then we have, at the moment, I'm just showing the results from Bob's paper. And so the line to focus on at the moment is the pink line, because the pink line was the graph neural network. And so if we do this algorithm or this exercise where we predict the dynamic propensity, but we only use the 0th order descriptors, so we only use the information we would have used before, then we get something that's actually pretty far away from what Bobst had. And so we see that, okay, we get some correlation between between what the dynamic propensity should be and what we predict, but it's not that great. And it's about the same as the support vector machine of Andrea Liu, which is not so surprising because that was also a linear kind of algorithm with the same kind of relatively similar kind of descriptors. But then we can go and add the 1st generation. So if we add the first set of averaging, what does this do? Actually, if we add one level of averaging, already we improve significantly. And so we get much closer to the graph neural network of Bobst. Then we can go even one further and we can say, okay, what happens if we add the 2nd generation? Sorry, I went the wrong way. If we add the 2nd generation, we go even further up. And so we essentially get with a simple linear regression algorithm, nearly or very, very close to the same ability to predict the dynamic propensity as this very complex graph neural network. And one can then ask, okay, well, what is the advantage? There's a number of advantages of doing this with linear regression. One is just the number of parameters. We go from 70,000, which is a tremendous number, to we can fit it with actually, well, we fit it with a couple of thousand, but we've also shown that we can get almost the same accuracy with a couple of hundred. So we can get away with many, many less. The computational resources are very different. You can fit this on your desktop or your laptop. It works very easily and you don't have to wait very long. You can do it very many times and test very many different kinds of structural order and how it correlates to glass. So that's nice. And it's also slightly more interpretable because, well, it's a linear regression. The connection is linear between these parameters that you have and your dynamic propensity. So in principle, it should open the door to more interpretability. And then one might ask the question, okay, so that's where we were, but that's actually already a couple of years, that's already 2021. So what's happened in the last 2 years? Actually, an explosion in this field has happened in the last 2 years. And so there's been a lot of people who've gone out and said, okay, well, can we not just improve the machine learning algorithm? And so actually in 2022, last year, both Shiba, which is a group from Japan, as well as Pesicoli, which is a group from France, actually looked at very advanced. We take our graph neural network and then we advance our graph neural network. And I'm not going to go through the details today, but you can make even more advancements on the graph neural network and ask, if we make advancements on the graph neural network, can we do better? And actually, they succeeded very well with this graph neural network. They were able to improve. If you like, this is our old linear regression, but it's actually very similar to the Bobst. So this is kind of what linear regression or what we were able to do in 2021 with also graph neural networks. And then in the last year, they've been able to show that by improving these algorithms or by going even more fancy with the graph neural networks, you can improve things. And actually, the group of Berthier, so Gerhard Young, a postdoc, has also shown that other variations of machine learning combined with inputting, instead of structural information or graph information, more physics-based parameters, was even able to do, well, in some sense, a better job at some time scales here. And so this has been, there's in some sense been an explosion of different algorithms in the last year for looking at this. This actually is a typo. It should say 2022, not 2023 there. So these came out last year. So we had the same question again. Well, okay, so is there a way of even going back and asking what kind of structural information might we be missing? And can we then again add to our understanding of glasses by adding new structural information that would allow us to fit the dynamic propensity even better? And so can we learn, can we learn even more? And of course, I wouldn't be talking about this if I didn't think the answer was yes. This is actually unpublished, but it should come out on the archive next week. And to answer this question, we came up with a bit of a different concept. So instead of asking about just the initial structure of the system, we asked about what we call the cage structure of the system. And so for those of you guys who are familiar with glasses, we had looked at the dynamic propensity earlier, and we said, okay, there's 3 different regimes of it. The dynamic propensity kind of had this shape. It went up and then it went flat and then it went up again. The first regime was ballistic. The second regime was caging, and the third regime was diffusive. And so if we ask, okay, well, what actually happens in the glassy system? Well, there's particles at the very beginning are away from kind of where they're expected to be, and they're going to hang out a lot in these cages. And so we wanted to add to information from the initial configuration, information about the cages that the system is in. And so we developed an algorithm which was able to identify the cage center associated with each particle. And then we added to the linear regression, in addition to all these structural order parameters before, we added information about the cage centers. And so instead of, for instance, just having information about the initial configuration, we have the initial configuration and this cage center, and as well as the vector between where the particle starts off and the center of the cage per particle. And then we fit again all of this structural information using linear regression. And we were very happy with the result, because we actually find with the simple linear regression and this simple change in our algorithm, which now incorporates information about cage centers, we are actually able to fit the data even better. And actually, if we see here, we have all of the blue lines here are then graph neural networks. Again, these are kind of the most new graph neural networks. And then we see that actually over basically almost all time ranges, carrying information about the cage centers actually allows us to improve the prediction of the dynamic propensity rather dramatically. It improves it the most in the caging regime, which is in this vicinity, but it also improves here, because before, this is our old data where we don't include information about caging. And if we do, then we actually increase the fitting significantly. And so actually, for me, this was a very nice take home, because one of the questions you might ask about all of this is, what can we learn from these fitting, or what can we learn from these predictions of the dynamic propensity? And I think that one of the things that we can learn is what's important for understanding the dynamics at different time scales. And so this is what we were able to kind of do here by what we put in. And in fact, we're even able to go a little bit further with linear regression and ask, at different time scales, what really truly is governing the dynamics. And what we found is that if you kind of ask, okay, what is the correlation between the forces that are the average force on a particle at the very beginning and its propensity? Well, you can actually do a very good job of predicting the dynamic propensity with just the average forces at very small time scales. It's not so surprising, but that's this blue line. Then if you only include the vector that connects where the particle is to its cage center, you can do a rather impressive job of fitting the dynamics. And so that's this red line, the distance to the cage center, does a rather brilliant job over actually a wide range in the whole caging regime. And then if you want to understand what's going on around tau alpha, the relaxation time, then you need really structural information. The most relevant structural information there is the structure around the cage center. And that's what this XS is. And so that works actually very well at this. We're able to even understand at different time scales exactly what parts of the linear regression are important for being able to do this very good fit that actually fits, well, at the moment, essentially, as well as any of the advanced machine learning algorithms. So before I sum up, I want to thank everybody who's been involved. This work has been going on for many years, so lots of people have been involved, but actually a lot of the work I showed today was done by Emanuele Boattini, who did his PhD in my group, and then that work has been picked up recently by Renske Alkemade, and essentially everything I showed you today was with close collaboration with Frank Smallenberg, who works at the LPS in France. But there's many, many people who have also been involved over the last year. And just to conclude, we showed that linear regression in combination with locally averaged structural descriptors can predict dynamics almost as accurately as the graph neural networks. We found that using information about cages is highly relevant, and this is very simple ways of probing glassy dynamics. And just one last take home, which is that I think even as we go towards more machine learning, I think we should not forget human intelligence in the way that we do machine learning. So that's my my last second of take home before the floor is open to everybody for questions.
Thank you very much, Laura. Very, very interesting, comprehensive, and also very detailed presentation. Now it's time for questions. There are at least 2 questions. Now is from Nikolai Kondratyuk. Can you unmute your mic and ask directly the question, Nikolai?
Yeah. Do you hear me?
Please.
Thank you. Yeah, Laura, thank you for the interesting talk. I want to ask if your methods could be applied for the molecular liquids with some structure, because like everything you told today was about Lennard-Jones-like systems where there are no like any structure, yeah, inside particles.
So where the particles, so you're saying, can it be used on particles that are anisotropic or have some shape to them? And then
yeah, in addition to shape, maybe some like maybe if we will consider molecular liquid with like maybe 20 atoms in molecule, for example.
yeah, so I mean that's kind of at the end of the day, if we're interested in a question about structure, then I'm going to kind of call that a shape, even if the shape is quite complex. The answer, I think the answer should be yes, to be honest. You have to, of course, augment it a little bit. And we've played with these kind of algorithms for recognizing liquid crystalline things, which are, of course, a simplicity version of, just something with an axis. Sorry, it blurred, so it's hard to see, but just something with an axis. But yes, of course, you can actually generalize these kinds of algorithms to materials that are more complex. The biggest question is then, what input do you use? So I mean, the type of dimensionality reduction and all of this methodology will work very well, but one really has to stop and think kind of with human intelligence about what is the best way of describing this environment? Do I want to describe this environment with the centers of the particles and some vector, or do I want to describe it with positions, with some kind of vector that describes the shape of the particle? I'd be happy to talk to you also longer during the poster session with ideas on that. But it's not something that you can just use as a black box and go, okay, everything you did can just automatically go onto this molecular scale. But I think it would be very easy to tweak to make it work as such. And we have definitely tweaked it to make it work for anisotropic colloids, but I think tweaking it to work for more complex structures would definitely be possible.
Thank you. So could I mail you
yes,
about
definitely.
the specific problem? Yeah,
definitely.
Thank you, Nikolai. Thank you, Laura. Now is Martin. Can you unmute your...
Yes, thank you, Laura, for this very nice and interesting...
sorry, Martin, whenever possible, I would ask to switch camera on possibly so we can see each other in face, in case it is possible. Otherwise, keep it off.
I am not allowed to switch on the camera, but sorry.
I think Andrea, they don't let it's only us who can.
Okay.
Yeah.
Next time for the next mix gen, I will ask a technician to allow attendees in case of question to switch camera on, because I think it's nice to see each other in face.
Yeah,
okay.
definitely.
Go ahead, Martin.
I have 2 questions. One is specific to these structural and dynamic correlations that you saw in the glass system, and now you basically supply to the field a number of new computer-found correlations. So what is currently what's the impression? What's the impact on the theory formation side there, and how do you expect this to be? So will ML definitely help to form better glass theories?
Will it help to form better glassy theories? I'm very much hopeful. I think I'm not going to bet in any direction there, Martin, but I think we're slowly being able to really probe glassy dynamics, probe what structures are related to glassy dynamics better. And I am hoping that at some point in time, this starts fitting into the theory more. I know that there's also work on machine learning connected to dynamics in the context of, for instance, using it to push theories even further. So there's work by Lisbeth Jansson's group where they've coupled machine learning techniques to mode coupling theory, and then started looking at how you can exploit machine learning to address even the kind of questions in theoretical, more in the theories themselves. I've been looking at it more from a structural perspective, but I think that I'm hoping that very soon we can start feeding into the theories more directly, but I don't have a better answer than that for you at the moment.
Thanks a lot. And then a question to the first part, so on finding structures and phases and
Yeah.
or mesophases or whatever. In the results that you presented, was there any surprise? So something like the ML algorithm found that you didn't really expect?
I think that I have to admit that to me, the biggest surprise that we found was that we found anything in the glass system. And that was not so much that I'm surprised that there are structural variations. I'm just mostly surprised that our algorithm was able to even start identifying those structural variations. I think that up until now, the place where we've been applying it kind of the most was with respect to nucleation. There was nothing I showed you today, but it's something my group has been doing locally. And I don't think we found anything surprising. I think more we couldn't find what we found less than I was expecting. And so we found less structure responsible for nucleation than I was actually expecting with these methods in the fluid. But something really super shocking, not yet, no.
Okay, thanks
it's
a lot.
more of a help. So it kind of things go faster rather than slower.
Yeah.
That's the biggest help that it's been.
Thanks a lot.
You're welcome.
Thank you, Martin. Thank you, Laura, for the answer. Now, Matthew.
Can you hear me?
Yeah.
Yes.
Can you? Yeah. Okay. Thanks for the very clear talk, Laura. Yeah. My question is a bit similar to the just question you had before, but let me phrase it slightly differently. So, what is the connection between your findings? I'm thinking about connecting structure in a supervised learning way with dynamics, with respect to previous work on trying to think about propensity from a more physical viewpoint. So I'm thinking in particular to, for example, the work of Orwell, where they're looking at vibrational modes and how it predicts propensity. That seems quite related to your idea of cage size. And the other thing is, if you look at longer times to alpha, there is also this literature on, locally favored structured and so on. So you tell us really what are the connections, or do we understand those connections or not? Because in terms of thinking about the question theoretically, it seems to be very important to make that bridge.
No, I completely agree. So maybe I'll answer your second question first, and I'm hoping that some of my backup slides that I was deleting from the talk today actually went to the back. So see if I find one. Please tell me I didn't delete it. Yeah, so you were asking about locally favored structures, and one of the questions that people have been asking in the glassy world before was, if I look at fast and slow regions, are there locally favored structures that are strongly responsible for that? I'm kind of phrasing it so that others might understand the question better. And one of the things that we also looked at in the context of this unsupervised algorithm was, okay, once we have these different regions, so the largest structural variation in my system, can I then start looking at what structures are actually more prevalent or more likely to be in the group A or group B? And then, to be honest, I would say that to some degree we found something that's very similar to what had been seen in the past. So if we look at, for instance, hard spheres or the repulsive particles, then we find that the regions which tend to be on the slow side have a lot of polytetral regions. So icosahedral, defective icosahedral, these kinds of structures, and then your kind of square pyramids and those kinds of structures tend to be more prevalent in the the grouping that ends up corresponding more to the fast particles in the longer time. And so there we see actually a strong connection between what was seen in the past, so icosahedral order, defective icosahedral ordering, and what we find, or what the unsupervised algorithm does. Does that make sense? Is that understandable, or is that?
Yes, and for vibrations.
For vibrations, I haven't looked.
Time.
Yeah, this is something we're really just digging into now. So I don't have a nice answer yet for you, but I think that is very much on our on our desk. Let's put it that way.
And like the previous questions that were asked, I also have another question on the first part of your talk.
Yep. No,
so it was on the unsupervised part where you identify two clusters of fast and slow particles.
Yeah.
I was just a bit. I mean, what surprised me that concerning the method is that the cloud of points that you showed us that were later cut in two by your sort of cluster algorithm was really monomodal initially. It didn't look like too nice.
It's not.
Too
No.
nice. And so I would have thought that then, you know, the choice of clustering method you use, I mean, that would be very sloppy, that you could find very different results depending on the clustering method you use.
Yeah. Okay. So that there's a bit of, it's to some degree gray. So what we can, yeah, I'm going back, but it's actually many slides back to go.
Yeah.
It's you're right that what we actually see at the end of the day is something which is actually probably better described as a very yeah, what do you call it, a stretched distribution rather than really it's not something with nice two peaks in it, for sure, in that sense. Well, at least the density distribution itself is not something where you see two groups in a very clear fashion. You can do some statistical analysis on it, and when you find that actually it's best fit with something like two Gaussians, which does, and there's measures, which I don't want to go into the detail here, we can during the poster session if you want, on what that would be. So I think that the argument that does two clusters fit it best, the answer seems to be yes, although one can have a longer discussion on that. I think what we do see, and what I would strongest say is that we do see a strong correlation between the largest structural variations in the system and the largest and the dynamical variations in the system. And that's something that's something that we can definitely pull out of this algorithm. And we've tried different kinds of clustering, and we've tried different, and that result is very robust. So we find that the structural variations in our system, the largest structural differences are definitely corresponding to the largest dynamical variations in the system, or the dynamical variations. But details, I agree with you on exactly how you cluster it. You might get mild differences, but the overall, no, I think that sticks around.
Thanks. I have a last question, but maybe I would let others ask.
Thank you, Matthew, for leaving the stage to the others. Thank you, Laura, for answers. Nikhil, please, one question, because there are many attendees who would like to ask questions to Laura. So please,
I hope,
one of the two, select the most intriguing one, please.
All right. I hope you can hear me.
Yes.
So I will. All the systems that you applied these clustering algorithms are having spherically symmetric potentials, right? So would they hold for non-spherically symmetric, or maybe systems like water, say, where there is strong hydrogen bonding, or silica kind of systems? Would they still hold the prediction of dynamic propensity from these sort of clustering algorithms?
Oh, wow. So yeah, sorry. So that's two different points. So, and I thought we were going in a different direction. So can we look at, can we look at different kinds of particles? If I go back to kind of the answer I had for the first guy who asked questions, and I'm sorry, I forgot your name, then the answer is that we can start trying to generalize the structural information as we put it in. And I think that the core of the question that you're asking is really, how should we even encode the structure if we're going to talk about something which has a type of symmetry to it? And so there it really is on a kind of system by system question. Is there structure on the object that we really need to encode in our local structure that's relevant? And if it is, then we need to definitely play with the way that we encode the structural information. I mean, if you have something that is kind of simple in some sense, here we have cubes. Cubes turn out to be close enough to spheres, and then you can use these basically blindly. But that's not true. At the minute that we had, rod-like particles, then you need to do something different. And then if you start talking about particles like, objects like water, then you have to again ask the question, am I capturing all the relevant information in the structural order parameter, or do I need more thinking before I even kind of try to apply it?
Right.
So the encoding of your system is really important.
All right. Yeah. Thank you.
Thank you, Nikhil. Michele, please.
Hi, Laura. Thank you. It was very Hi, it was very nice, very pedagogical talk. And I very much sympathize with a lot of your conclusions about how there is kind of a trade-off between the interpretability of what you do and the level of sophistication. And so I would say that this is not something which is very specific to soft matter. It's quite general. But so the question that I have for you is whether whether basically you can really extract the new insights, whether there is also kind of a trade-off, not only between the complexity of the model and the interpretability, but also between the heuristic power of the data analysis and the interpretability, in the sense that my impression is that very often when you have something which is very interpretable, it tends to rediscover something which is in line with the sort of general expectations and the general wisdom of the field. So do you have one example that really stands out in which you were able to discover something that was going against the grain of the typical...
Ooh, that's a tough one. Going against the grain, I'm going to say no, not in a dramatic fashion. I think it opens the door. I think I've more found it something that's very nice to open the door to doing things more rapidly, if you like. I think with respect to things like fitting the dynamics, I was very interested, to be honest. I learned a little bit more about how information was processed, even in a graph neural network, by going to simpler system or simpler ways of representing it. I think that there we learned a little bit about what kind of information we need to capture if we want to describe the dynamics better. Well, you can ask the question of what are you getting out of that? And I think at the end of the day, some of what we get out of that is even new insights into maybe the way that we looked at systems in the past. So going back to the question that had to do with caging, I think that there is actually something very interesting there, but this is something that we will be looking at in the next little while. But it's not something that I don't find it so much shocking as maybe a new way of looking at it that provokes at least my thinking to go in a slightly different direction, but not a tremendously different one, is my honest opinion.
And I mean, just a very quick follow-up. Do you think that actually that actually this is a consequence of the simplicity of the models, and that somehow going towards deep models that are more flexible? Often people who talk about deep learning speak about emergent behavior in the network, and soft matter is is home to emergent phenomena, one of the main examples of emergent phenomena. So do you think that somehow
Yeah, so I mean, I have to admit that my playing thus far has a little bit in the other way around. So we get advanced machine learning methodologies, and then the question is, can we go back and kind of, with a bit more understanding of our system, can we get the same thing out of simpler models? So the blue is actually quite deep. The blue lines here are all actually very deep and complex machine learning algorithms. And so can we then somehow, using our understanding of the systems, or even learning from what the networks were doing, can we then incorporate that into structural order parameters that then give us more information? That's kind of more the direction I've been moving. And that it definitely has been able to do. So the graph neural networks have been a great place to look to try to understand a bit better what structural information do I need to capture, as an example.
Okay. Thank you,
Laura. Thank you, Michele. We go quickly to the other questions. We have four more questions, and please be pretty quick in asking. And Laura also.
I'll try to be short. Yeah, sorry.
Bart, please go ahead.
Thanks, Laura, for the amazing talk. I'm more of the condensed biophysics, so usually my environments are very complex respect to this, but it's nice to see sometimes the simpler things to understand also the concepts better. You said that you mainly looked at structure to sort of get a good theory for the dynamics, and I was wondering, and you also started to correlate it in your first examples where you showed that the structure can like it has a good correlation to what the dynamics behave. And I was wondering if you would combine sort of a small sliding windows of your understanding of dynamics into your predictor, right? Does that actually improve your boundary even more? So would it increase your contrast sort of being able to draw lines around certain shapes? Then, or did you look into that?
I'm not sure I completely understand your question, if I'm strictly honest with you. So you're saying that if I were to put dynamic information into my structural order parameter, would I get better structural deviation?
Well, so let's say you make this sort of neighborhood description of your particle, right? And then you use that. But you could also say, I look at the dynamics of my neighborhood of a certain amount of time. And does that actually improve? How much does that? So first you looked at how do they correlate, right? But you can also say, what if I pile them both up? Like, what if it increased my resolution of sort of drawing the boundary?
This, if we're interested in structural kind of different regions of my system, I could imagine that would be something that's possible. I've never done it.
All right.
Just go flat. No, I've not done that.
Okay, cool.
Intriguing, but not done.
Yeah, I hope you did. All right, thanks.
Thank you, Bart. Alessandro? We can move to the next questions. Guido, Raus, please select one of the two.
One of the two, yes. Let me go back. Sorry, where is it now? Yeah, okay. My question is, why concentrate only on the structure? Would it be legitimate in a machine learning model also to incorporate information about energies or forces? Would that be cheating? I mean, for example, as an example, you could have, I could show you a picture of Lennard-Jones atoms or Hart spheres, and the pictures would be the same. But the energies, the forces would be different. And as a consequence, also the dynamics would be very different. What is your opinion about that?
I don't think there's any, I don't think there is even the possibility of using the word cheating. I think we're trying to understand something, and knowing what you need to put in to do a good job of predicting the dynamics, I'm hoping gives us a bit of information, even if sometimes it's repetitive of things we kind of expected. The plot I show you here is what happens if I correlate forces to the dynamic propensity, and what happens if I include that. And so we've played with this as well, because I think these are interesting questions. What happens if you're from the glassy community? You can talk about the inherent state. What happens if I throw the inherent state in there, which is associated with the structure in a different way? I don't think any of this is cheating. I think it's just ways of probing what pieces of information are relevant when, and it's just different ways of accessing that question, would be my take. The work of the paper by, and again, I've made a typo here, it should be 2022, but the work by Young has looked at looking at machine learning with a lot of the input coming from kind of physical features of the system. And I think that's very nice work and quite relevant.
Okay, thank you, Guido. The very last question from Alessandro, sorry, he wrote me that he cannot switch mic on, so he's very curious about the strong dependence of correlation upon time scale for different models, which is the cause for this effect.
I'm not sure, now I can't ask him what he means more clearly, sorry.
About the strong dependence of correlation upon time scale for different models.
For different models, so in the sense that different models are, I'm hoping, and I'm going to guess what I think the question meant, so that if I look at, for instance, the yellow line here, I see that the correlation is very good at, and tau alpha is around 10⁴, so is around the structural relaxation time, and it's a little bit later. And if I look at another model, I see that there's a weakness. I think that is really associated with the strengths of these machine learning algorithms. And to be honest, looking at these weaknesses are kind of how we've been approaching, how do we improve it? So why is this algorithm weak in a certain area? I mean, one of the questions we had recently was, why is it that graph neural networks do ridiculously well at these really short timescales, and is forces sufficient to explain that? And it turns out that forces are not sufficient to explain it, because if you add forces to a linear regression model, you still don't get anywhere near the ridiculously high peak here of the graph neural network. So I have guesses on why that's the case, but I think that's an interesting question. Why, and can we capture that in an understanding? I hope that was the question, Alessandro.
Yeah. Well, he said exactly this was the meaning of his question. Thank you very much, Laura. Thank you very much to the participants. So many questions, very, very interesting discussion. We are 4 minutes late, and so we move quickly to the next speaker, to the next talk, Alessandro Coretti. Please, Alessandro, the stage is yours.
Yes, good afternoon. So let me first of all share my talk and just a confirmation that is working and that you see that. Can you now see that?
We
and
can see perfectly and we can hear you.
Okay, great.
Well. So please go ahead. Take
Perfect. So good afternoon, everybody. Thank you very much to the organizer of this very nice event. It's always a pleasure to be part of SICAM events. And so what I'm going to talk about today is a different kind of neural networks with respect to the one that we have discussed in the previous talk. And I would like to thank also Prof. Pilion for being so complete in the presentation of neural networks. So that's a bit less work for me. Thank you very much. So first of all, let me take a minute to acknowledge the people with whom I'm working. So Sebastian Falkner, which is a very talented PhD student in our group, and Christopher Delago, who's the PI of the group. And let me take a minute to remember also Phil Geisler, who suddenly passed away this summer, and he was he was involved in the project from the very beginning, and I didn't have the chance to really meet him because of the COVID situation, and he was working at Berkeley in US, so you can imagine that coming here with all this situation was it's not very feasible, but we had a lot of very nice discussions, and his contribution to these projects were incredibly important, and we are all very sad that he suddenly passed away this summer. So yes, so this talk could be mainly about machine learning and not a lot about soft matters, but anyway, this is what it is. So whenever we think about machine learning, well, at least me, and a lot of what also we have seen in the previous talk can be fit into the category of labeling problems. So we basically have a huge data set, which in this case can be handwritten numbers or like pictures of clothes, and we want the network to basically label these numbers or these clothes. This is one of the classical problem that machine learning approaches it. But in this talk, we are not talking about that. So we're talking about different problem here, which goes into the class of the generation problems, which is basically given some form of random noise, of a uniform or Gaussian distributed random white noise. We want to generate something out of it, and for example, a picture. Like what you see here, this is a machine learned, let's say an AI generated image, or for example, some speech, some text. So these kind of problems have been actually have been brought to the attention of the public in recent times, from OpenAI, basically, which has released this DALL-E #2 and ChatGPT. You have probably discussed about that, and what they do is basically very close to what we will discuss today, but for images and text. So you probably all know DALL-E, and what happens is that you give them some text, you give the machine some text for example, like draw me the headquarters of SIGAM and the PFL in Lausanne. And what happens is that the network generates some picture, which I don't know. I mean, to me, if you are familiar with bathychemy at the PFL, it really resembles the view that you have when you're coming back from having lunch, for example. Or this is also another picture that the network has generated, in which, again, I think you can really find something very close to what it is. And finally, this is not really bathychemy, but it's very close to another building at the PFL, which is actually what you see when you go out from SICAM. So this is really interesting. It's a lot of fun, and I really recommend, if you have not played with that, I strongly recommend you do that, because it's really a lot of fun. And same about ChatGPT, which is even more recent. But in this case, you ask the network to produce some text, some written, let's say, essay it's really controversial. But this is what happened if you ask the network to generate some brief history of SICAM. And well, this is quite accurate actually, except for one point, which I'm not sure. I didn't find any. I tried to fact check that, but I didn't find anything about the fact that CHECAM has its origin in the work of European Physical Society and European Chemical Society. So maybe someone more expert than me in the SICAM history can confirm that, but I think this is a mistake. So be very careful when you use that. But this is a very nice feature. This is something that has been generated out of the blue. And the cool thing about ChatGPT, and here we're really playing now, is that it actually remembers previous questions and previous answer that it gave to you. And so you can actually really, I don't know, mimic a dialogue with them. And it's pretty, it's pretty impressive, I think. So how do these generative model work? Well, the idea is the following. You have a distribution, that we can call a prior distribution. And then you want to transform the elements sampled from this prior distribution in another different distribution that we call a posterior. So you get the elements from which are sampled from the prior distribution and then lives in something, they live in something that we call the latent space. And then you feed them into a function that is what the network actually needs to learn. And hopefully the whole goal of these models is that they transform the samples, the elements sampled from the prior distribution in elements sampled from the posterior distribution. That in our case live in configuration space, but you can think about that as what the examples that we saw before. So for example, like the image space or the text space, something that is what we want to actually generate. Now, of course, in the case of images and text, the training is done by example, in the sense that we don't have any knowledge about the analytical form, for example, of what is the distribution of images on the web of dogs, for example, or the analytical form of the distribution of the text talking about the SICAM history or something like that. So basically you have a huge data set, the network takes some examples from the data set, try somewhat computes a distribution and try to match the two distributions with the transformation that the network has. The very important thing of these networks is that of these generative models, of these generative networks, is that what they generate, it's not a part of the training set that they've seen. This is the whole point, right? We want to generate something that it's not in the data set. So basically what you've seen before, the images and the text that you've seen before are not something that, the text is not what you find on Wikipedia. Of course, it's kind of guessed from there, and Wikipedia is definitely a huge data set for that. But it's not something that is there, so it's not an element in the data set. Here you're seeing some elements, this without the yellow border. It's basically some elements that have been generated using generative models, and what you see here with the squared in yellow basically are the closest element in the data set to the generated one, to the neighboring one, actually. And you see, in the case of handwritten, they're quite similar, but if you take a look at the images, you really see that it's not the case. They are different. They're very different from what they see in the data set. They are new elements. So how can we use them in statistical physics? Well, we all know that in statistical physics, we have the sampling problem. In computational physics, it's quite painful to generate configuration. Yes, we have methods like molecular dynamics or Monte Carlo methods or all the evolutions from these to generate samples. But the samples, they have some, these methods do not come without drawbacks, right? Because they are both based on successive update of previous configurations. And so samples are correlated, they're expensive because you need to perform a lot of steps to get something which is independent, or at least correlated for what you had before. So it would be great to be able to use these generative models in statistical mechanics to solve the sampling problem. And one architecture that is particularly suited for this, it's what is called normalizing flows, which will be the object of our next couple of slides. So the idea of these normalizing flows is that you sample in a two-dimensional space, you sample some elements, you take some elements which are sampled from a Gaussian distribution, normalized, for example, and then you try to map them to some other configurations which corresponds to configurations which are Boltzmann distributed and are Boltzmann distributed with, for example, with this particular shape. This would be the goal. So we sample from a Gaussian and we get something, we train the network to give us something which is, on the other hand, Boltzmann distributed. Why this would be great? Well, it would be great for more than one reason, but I'm talking here about two main reasons. Well, the first reason is that we know how to, for example, how to generate the correlated samples from a Gaussian distribution. And that means that if we generate the correlated sample from a Gaussian distribution and then we transform that, we get something, we get Boltzmann sample with Boltzmann distributed sample, which are decorrelated. In theory, solving the sampling problem. Now, it's not that easy, we will see that. But in theory, this would be great. Also, another very nice feature is that like close points in latent space could actually correspond to very different points in the configuration space. And so basically performing a random walk in latent space and then going back and forth from the latent space to the configuration space could actually be a very nice way of, like exploring the potential landscape. And this would be great. Now, we need to be careful though, of course, because, for example, we are in a very different situation compared to the image and to the text or speech generation, right? Because for this particular case, we have actually something like an analytic expression of what is the target distribution. So in principle, we would like to use that information because we have the expression for the Boltzmann distribution. On the other hand, we would like not to rely too heavily on examples from the Boltzmann distribution of the system that we want to simulate, right? Because if we have a lot of samples, so maybe also decorrelated samples from the Boltzmann distribution that we want to simulate, well, at that point, it's not really interesting to generate new ones, right? I mean, that would be a bit of looping around. So we want to highly use the fact that we know the analytic form and not a lot of samples from the target distribution. And finally, whenever we have to deal with the physical and statistical distribution, we really need that the distribution that we get out of the network needs to be exact. I mean, it doesn't really matter if the image that we get for a dog out of the generative model, it's not exactly sampled with the right weights from the distribution of the images of the dogs. I mean, as long as we identify that as a dog, it's all right. But that doesn't happen with configurations from the physical space, because our idea would be that we compute observables out of that. And if we compute observables out of configurations that are in configuration space that are not correctly weighted, we get wrong observables. So that's bad. We don't want that. But normalizing flows are actually the perfect tool for this. And I will give you a quick overview, not to be late and maybe telling you about some results, but then of course in the Q&A or poster session, we can discuss more about how these normalizing flows actually do this. But the idea of normalizing flows is that we have latent space, which we will denote by Z, and where samples are taken with a certain distribution, which is known, let's assume the Gaussian distribution that we discussed before. And then we have a configuration space where again, we have elements that are distributed with a certain probability that we know, but we don't have a lot of these elements. And we want to use the fact that we know the analytical distribution, the analytical form of the distribution of the elements in the target space, so here, to train this network to transform samples from one to the other. And we can do that. In particular, we can do that with something that is called training by energy, which basically does exactly that. So basically, it samples from the latent space, it tries to transform, compute the distribution, the energy in practice of the target space, and then it compares what you have and what you should have, and basically does the training. So in that sense, it uses the information that we have on the Boltzmann distribution. Now, this is usually not enough. This is usually not enough to do that because, for example, that tends to focus the transformation on areas of the configuration space that are very low in energy, that correspond to one minimum of the potential energy surface, but maybe not on all of them. So we also need a bit of samples, and that's from the configuration space, which are hopefully a bit quite well decorrelated, but not a lot of them, in such a way that we can, let's say, help the training in the other direction, and to basically use this training to map the whole potential energy landscape. This is what normalizing flows can do, and this is what is called training by example, and is exactly the same kind of training that we use for example, for generative models in the speech and image recognition. But this is not the only one. So we also have an alternative, and we should strongly rely on that. Once the training is complete, what we can do then is that we can sample from the latent samples from the latent space. We can feed these samples into the network that has hopefully learned a very good transformation, and it will give something that is hopefully very close to the target distribution that we want to obtain. But it will not be perfect because of many reasons, because there would be still a bit of a trace of the original distribution, for example, or because simply the training is not perfect. But normalizing flows are great in this sense, because the fact that the transformation is invertible and the architecture of the network is built in such a way that the transformation that is learned is invertible, then what we can do is actually we can unbias the distribution that we get out of the network, and to get something which is proportional to the real Boltzmann distribution. That is why they are such a promising tool for statistical physics, for configuration generation in statistical physics. The only important thing is, again, that for unbiasing the final distribution and for the training in both directions, it's very important that the network is invertible. And this is a very good point, and it's also a bit of a limitation of these models, because that means that you have to go from something which is you have to connect stuff that the spaces that lives in the same dimensions. So that's a bit of a limiting factor. But Boltzmann generators or normalizing flows for generating the Boltzmann distribution have been used, and there is this pivotal paper by Frank Noé and co-workers, which came out on Science in 2019, and let's say has started a whole new field of research in these generative models or normalizing flows for statistical mechanics. But also Google, in the DeepMind, at least, in particular with Peter Winsberger and co-workers, have been super interested in studying these models for statistical physics. And also in our group, we have studied and we have actually applied these models with Sebastian and other people from our group to the simulation of to the sampling of rare events. I don't really have time to discuss that today, but we have an archive out about this, and that's also a very nice application in which we use normalizing flows to generate configurations, but we need to condition them. And I strongly recommend that you read this paper if you're interested in rare event sampling, because this paper is great. And but what we also follow another line of research in the framework of normalizing flows, and is what happens if we, instead of using something that we can simulate very easily for the prior, like a Gaussian distribution, in which we can sample very easily elements, we can, what if we choose for the prior something different, something like another Boltzmann distribution? Would that be possible? So would it be possible to train a network, a normalizing flow in particular, to go from samples that are elements or configurations that are sampled with one Boltzmann distribution to elements that are sampled with a different Boltzmann distribution? Is it possible? Well, I mean, for this very simple model, this is possible. This is actually, these are real data obtained from a normalizing flow trained for the purpose. And but this, if we decide to do that, why is the case? Okay, yeah, we like to do cool things, of course, but also, I mean, is this useful for something? Well, I mean, first of all, we thought about something and how this could be useful. And the thing is that, for example, for liquid system, training a network, a normalizing flow to transform from a Gaussian to a Boltzmann distribution of a liquid system, that's very hard because a liquid is very, very different. It's distributed very, very differently from a Gaussian. And for solids, for example, that can be done, and this has been done in this paper from Birsberger and co-workers, but in which still they have included in the prior, which is still Gaussian, but they have included some physical intuition in the fact that basically it's a lattice of Gaussians which are distributed in the same way as the target solid is placed. So you have Gaussian on the prior side, you have Gaussians that are distributed around the lattice sides of what you want to have in the final distribution. If you try to do that for liquids, that becomes a bit more complicated. So we wanted to do that for liquids, and we tried this. And also another reason why we wanted to do that is because maybe we can use this approach to actually move from situations in which we are simulating one system using a very, let's say, a not super accurate model, but a very cheap one to simulate. And maybe we want to simulate, to transform the configurations obtained with this very, let's say, not very cheap model in something which it's more difficult and more expensive computationally to simulate. So, for example, we could think about simulating something with force fields, all atom simulation, and then to transform that in in configurations that have been obtained using DFT calculations. And we could think about this in a whole hierarchic way, so that we basically start from coarse grain, we go all atom, and then from all atom we transform to ab initio, and then maybe we also include the nuclear quantum effect. And at that point, once we have a very, let's say, at the head of this hierarchy, we have a very, let's say, approximate method. Maybe at that point it would be also possible to connect that to a real Boltzmann generator, to something that samples from a very easy to sample distribution like a Gaussian. That would be the goal, and that is what the project is about. But let's go by small steps, and let's see, first of all, if we can do that, for example, for liquids, going in between, transforming between the same kind of models. So, for example, let's see if it's possible to go force field to force field for liquid system. And we've done that with liquid Lennard-Jones disks. And in particular, we trained the network to move between two different Lennard-Jones simulations with different parameters for the epsilon, for example. So basically to go from this form, the blue line of the potential, to the orange line of the potential. So basically just same potential model, but with different parameters. And then we also tried to do that with a bit more sophisticated, in a bit more sophisticated way. So basically removing some part of the target model. So, for example, we tried to move from a WCA, where only the repulsive part of the Lennard-Jones potential is considered, to a real Lennard-Jones system. And we have computed some observables in this way. So we have trained the network to do that for the two systems. And we have computed like potential energy distributions of the configurations that we have obtained and radial distribution functions. Now, Let me just focus 1 second on this plot, because this can be sometimes misleading to read. And so let me guide you through what is this plot telling you. So let's consider only the case in which we move in one direction. So in this case, we're moving from Lennard-Jones at standard Lennard-Jones to a different Lennard-Jones, which is basically with a higher temperature. So the energy distribution, the potential energy distribution that you're seeing on this plot are all computed in using the energy of the target system. So this Lennard-Jones potential here, basically. So what is changing in this plot are actually the configurations that are used for the energy computation. So in blue, you see a reference set. That's easy. Basically, you have some Monte Carlo simulation, or yeah, in this particular case, it was Monte Carlo simulation performed with the target energy. So that is exactly what we want to obtain. That's a reference. In yellow, what you have is what we have done to produce this yellow distribution is the following. We have done some Monte Carlo simulation using this time the energy of the original system. And then what we have done is that we have computed the energy of these configurations using the energy of the target system. So basically, we have taken the configurations that are coming out of the Monte Carlo with the potential energy of the original system, and we have computed their energy without doing anything in the target system. And this is what we get. And you see that the two distributions are quite different as expected, because these configurations are obtained with different potential energy. So it's of course the case. And what we are mimicking here is basically what happens if we assume that the network didn't learn anything. So basically the transformation that we are applying with the neural network is the identity. This is basically the potential energy distribution that you would have obtained using the identity. And then we have trained our network, and we have applied the learned transformation, the transformation that the normalizing flow has learned to these configurations here. And what you get is the green curve. And now you see what I mean when I said that there is a residual bias arising from the regional distribution in the learned transformation by the network. You see that after the training, what we obtain is a distribution of the potential energy, which is a bit in between the two. So it's definitely going in the direction of the reference that we want to have, but it's still different. But then the reweighting or the unbiasing procedure that I told you at the beginning enters into play. And what happened is that the reweighting those configurations, the configurations that have been transformed by the trained network, we get something that is basically superposed. And you can also compute the energy, the average energy that you get from these two distributions, and you see that they are extremely close. We have done that for different observed. We have done
Alessandro, sorry,
yes.
Can you go quickly to the conclusions.
Yes, I'm almost done.
Because we are running out of time, and
yes, I'm almost done.
For further discussion. Thank you very much.
Yes,
sorry.
because basically we have done that for the potential energy distribution and for the radial distribution function. You see exactly the same thing, and we have done that for the other numerical experiment, which is basically from WCA to the Lennard-Jones, and we also get very nice results. And now the last thing that really 30 seconds, give me just 30 seconds to conclude. It's basically, we are going a bit further, what we have done, so all atom to all atom, but what we're doing is now all atom to ab initio simulation. Now, is this useful? Well, yes, because imagine that you have a force field MD molecular dynamics simulation, you get an initial configuration, and then you start a trajectory using the force field molecular dynamics, and then you sample configurations each in such a way that they are decorrelated from each other. So at this point, you have n configurations which are distributed with the distribution of the force field. And then you pass those configurations inside the normalizing flow. And what you get, hopefully, is a number of decorrelated ab initio DFT configurations that are now distributed in the way that the DFT configurations will be distributed. Of course, you don't use the whole trajectory because otherwise that becomes super expensive, because when you compute the reweighting factor, you also need to compute the energy in the target space. So you only do that for the decorrelated configurations. And we have done that for 32 Lagrange particles with some fitted parameters that we have fitted such a way that the potential energy were really close to each other. And we've done we have transformed that to match the reference, which was the same 32 aluminum particles, which were simulated with some GGA potential. Same sampling, same temperature. And what we have, this is very preliminary, but what we have is really going in the correct direction. So you see in particular that the potential energy distribution of the force field it's really well superposed to the reference distribution. The other way around is a bit more complicated, and we could have some problems there, but this is something that we are trying to solve. So yes, I'm done. No conclusions, because it's we can probably discuss that, and I just leave you with some references. Very nice review about normalizing flows here. This is the previous work that has been done on normalizing flows in statistical mechanics. So we have already seen these 4 papers, and this is where we discuss the Boltzmann to Boltzmann approach. And sorry for the delay, and thank you very much for your attention.
Thank you, Alessandro. Thank you very much. There is time for a couple of very quick questions, if any. Please type your name in the Q&A, and then I will leave you the stage. I have very quick curiosity, Alessandro, just
yes, please.
To ask a question, and then we can move to the other speaker. Have you planned to measure distribution distance with methodology such as optimal transport or something similar to the geodetic distance between distribution, if needed? For example,
no, but the way we computed, I see your point. The way we compute the distance between distributions is basically based on Kullback-Leibler divergence, which is, I would say, standard practice in machine learning, in this kind of machine learning. But of course, different metrics are also possible, and that would be definitely a good idea to also investigate them. And I think that they have also done that in the framework of the study of normalizing flows alone. But in the framework of the use of normalizing flows for statistical mechanics, I think that this is quite a state-of-the-art to use Kullback-Leibler.
No Wasserstein distance, for example.
No, not that I know. But
okay, thank you.
It's possible that someone has tried that.
Okay, thank you. Thank you again, Alessandro.
Thank you very much.
The questions are moved to the poster session, and now Atreyer, the stage is yours. Thank you very much for being here.
Let me share the screen, and can you see my screen?
Yes, we can see and we can hear you very well. Yeah. Please go ahead.
So first of all, I would like to thank the organizer for choosing my poster for a talk. And I'm a postdoc at Max Planck Institute for Polymer Research. And today I'm going to talk about glass transition in polymer melt using data-driven methods. Now, Laura gave a great introduction of supercooled liquid. So if you start from a high temperature liquid and cool it faster, then the system is not crystallized. And somewhere here, you can see the dynamic slowdown of the dynamics. And on further cooling, the supercooled liquid forms glasses. And this glass transition temperature, the temperature at which the supercooled liquid form glass, is not a fixed temperature. It depends on rate of supercooling. Now, looking at the overall structure, that doesn't change that much while reducing the temperature, but the dynamical property changes orders of magnitude that we all know. And there are recent work, what Laura was showing, that maybe the overall structure doesn't have that information, but local structures are connected to the dynamics. So today, I'm going to talk about a very different class of glass former. Those are like polymer glasses. Now, polymeric materials also form glass, and below glass transition temperature and above glass transition temperature, the material property changes a lot for polymers. So the polymers are stiff below TG, whereas it's like more rubbery above TG. So it's important to define the glass transition temperature for polymeric material. And the standard way of doing it is usually from the change in the specific volume or the change in the density. So today I'm going to talk about this. This is a work with simple bead spring model, coarse grain bead spring model, and there are 2000 chains in the simulation box, and these are like computer simulation result, and each chain has 50 monomer, and the same sample is prepared with a constant cooling rate. So with this data, people have already reported the glass transition temperature using based on different macroscopic property or global property of the system. And also one can calculate the displacement of monomers, and it shows a very similar behavior in the case-like behavior in the glassy state. And from there, one can also feed that data to a VFT kind of fitting and get a divergence temperature. So you really need long simulation, and depending on fitting parameter, you get a divergence temperature from dynamics. Now, our idea was, can we determine the glass transition based on purely structural fluctuation, where we can feed in the information about the local microscopic detail? And for that, what we have done from this whole simulation box, we have chosen one chain, for example, and use the monomer distances as a feature to our dimensionality reduction method. And then we see the lower dimensional projection, and then we apply some sort of clustering to see whether we can separate out this liquid state from the glassy state, whether these states are physically meaningful or not. So this is the overall idea. Like based on the simulation data, we want to have some information, local chain fluctuation, that will be feeding to our dimensionality reduction methods. And by distances, I mean the internal distances. So if my chain consists of 50 monomers, then I calculate all internal distances between each monomers, and that goes as an input to the method. Now, for the first case, and we used for the dimensionality reduction method, we use the simplest one, PCA linear. That's because we want to know what's the meaning, what's it's going on within the system. So we made our method as simple as possible. So for the first case, we took one chain and combined the data for all the temperatures, going from high temperature to low temperature, and see the chain's fluctuation. And this is for taking randomly one chain from the whole simulation box. And this is how the projection looks like. Now let's go back. Let's just show a few data and try to understand what this projection means. And I'm focusing on 3 temperatures. So at high temperature, so this is if we apply principal component, and the data is projected along the leading PCs, PC1 and PC2. So at high temperature, so each point in the configuration space represent one configuration in chains configuration, one of the chains configuration. So the chain is moving rapidly at high temperature. That's why it is like exploring more phase space. While at the intermediate temperature, the dynamics is frozen. That's why it's exploring less. And eventually when it is glassy, then everything is frozen. So it's stuck together. So the chain is not moving at all. It's vibrating around something. So we get a frozen state like this. Now let's go back. And this is the result for all the temperatures. This is a PC projection. And as you can see, even based on the first principal component, we can already separate this low temperature state from the high temperature state. That means the PC can be, this for leading principal component can be looked as an order parameter to separate this low temperature state to high. And to generate, to classify that, we applied some density-based scanning, like clustering algorithm on these PCs, and see how the clustering looks like. And this DB scan groups together the data based on some density criteria. And as you can see here, all this high temperature part comes as a noise by the method, and this low temperature part where the system is frozen comes as a cluster. So one can check the change in the cluster ID going from this noise state to this glassy state and as a function of temperature, and that can be taken as a parameter to look at and see the transition. So this is like something I was talking about. So we check the cluster ID and see at what temperature this going from liquid state to glassy state is happening. And of course, as I said, I did it for one chain, but this is what we should not look at. We have to have something that's averaged over all the chains present in the system. And that's why we repeated this analysis for all the chains and then did the clustering for every individual chain. And this is the average cluster ID as a function of temperature. And you can see that it goes from liquid state to the glassy state pretty close what has been observed based on the microscopic detail like volume or specific volume or density jump. Now we also have an error bar because there are many chains in the system, and as it has, you can see during the transition, the system finds it's most hard to group the data into two different states, whereas in the extreme ends, the grouping is much clearer. But in this way, we can predict the glass transition temperature from the change in the cluster ID. Now, glass transition temperature is something that depends on the observation time. So that's why we thought of doing the same analysis depending on different observation time frame in the system. And we found like if we wait long enough, then the transition becomes sharper. And if we predict, like if we plot the glass transition temperature for different time window as a function of 1/t, then we observe a very nice linear fit, which can predict the glass transition temperature in an asymptotic simulation like infinite simulation timeline. And that was a very interesting result. That is what we were, means our simulation data is relatively short. And from there, we can predict what will happen at infinite time, which was very interesting. Now, this is a whole idea. So from the whole box, we take a chain and then do dimensionality reduction, then average over all the chain and get some property to quantify TG. Now, what if we throw all the chains present in the system at a time? So instead of taking one chain's fluctuation, what if we feed every chain's displacement at the same time? Then it's something like a blob. And as a function of temperature, we do not see any difference. And this is something people observe by measuring structure factor or something. So if you give everything as a function of time or while it's going as a function of temperature, while it is going through glass transition, there is not much structural change. So you do not see anything. But individual chain has that information. So by doing this kind of analysis with individual chain, we can pick up this TG nicely, which is totally smear out if we take all the chains at a time. Now, in the next analysis, instead of so far we were treating all the temperature data all together and feeding that into my PCA, but now we treated individual temperature separately. So in that way, high temperature has no information about the low temperature or vice versa. So each temperature is treated in the principal component analysis separately. And this is how the projection looks like along this principal component 1 and principal component 2. Now at high temperature, the chain is moving a lot. So there are like a lot of conformational fluctuation. So that's why this is what can be explained. But when it is going through the transition, we observe a correlated motion or like a U-shaped behavior. And at very low temperature, this is again all jumble around together. And this is because our data is standardized. So we standardize the data at each temperature. So the standardized means it's mean free and standard deviation is 1 when we feed that into the principal component. Now that's why this high temperature and some random fluctuation at the very low temperature looks visually similar, although they are coming from a two different kind of represent two different kind of physics. At high temperature, there are like conformational fluctuation, whereas like at low temperature, if the chain is frozen, so it's just some random vibrations that PCA picks in. But this is done. This is the presentation for one chain. We again wanted to quantify some quantity and average over all the chains and get some meaningful property which doesn't change as a function of which represent the whole system. And for doing that, we plotted the first principal eigenvalue and then the participation ratio. So participation ratio can be it's connected to the dimensionality of your data. So higher the participation ratio means you need more and more dimensions to represent the data, to explain the data. Whereas the lower participation ratio means the data is correlated, you need less dimension to represent the data. And what we found at higher temperature, it starts with some participation ratio value, and then while going through the glass transition, this reduces, and eventually at very low temperature, the participation ratio is again high, and this is because now the system, the method is picking up some random fluctuation around when the chain is frozen. But interestingly, there is a non-monotonic behavior both in participation ratio and in first eigenvalue, which is like very close to the glass transition temperature, what has been found earlier by treating the data differently. Okay, so this was the whole idea. Using the different data, we tried to predict TG. And then this was done for a chain length of 50. Then we tried to use the subset of the chain from this subset of the monomer from the chain. And these monomers can be selected from the end or from the middle part of the chain, but result doesn't change much. So what we found, when the number of monomer is smaller, then the separation between this liquid and glassy state is not that prominent. And one can do the similar analysis with combined data or individual temperature data. And what we found, that when the chain length is of the order of like around 30, then the separation is prominent, and then this doesn't change that much when we increase the data. And the entanglement length for this polymer melt was reported around 28 before, so which is very close to the value where we got this separation. Then we tried to understand what are the meaning of these species. And then we looked at the eigenvectors, but it changes a lot depending on different chain. We have like 2000 chain in the system, so we do not see any pattern in the eigenvectors in that way. But what we tried to measure, what are the distances, like the internal distances that we feed in as an input to which the leading species are mostly correlated with. So we calculated correlation coefficient with the leading species and the input projection, and calculated the distance from there. And we found like it's not the end-to-end distance or like largest distance, those are connected with the correlated with species, rather it's something intermediate. And since we have like a lot of chain in the system, is distributed all over the places, so there is no characteristic distance which is important for every PC. It depends on really which chain you are looking at, and it's distributed all over the places. And we also try to calculate the correlation coefficient with physically motivated quantity, what people in polymer physics look at, like radius of gyration and end-to-end distance. And our first principal component was highly correlated with these distances. And then we also tried to project the data of end-to-end distance and radius of gyration for the same chain for which I was showing the PCA projection into in this space. Like we plotted the radius of gyration and end-to-end distance for the same chain over different temperatures. And you can see that, when it goes to the low temperature, it's not moving much, but the separation is not as clear as what we got from the PCs. And we did a similar average cluster ID analysis, and the error bar associated with the clustering is much higher in this space. If you compare to the PC space was much cleaner in that way. So this is the overall idea. Based on purely structural fluctuation, we identified some order parameter which can separate the low temperature part from the high temperature part. And this was archived last December. And then the overall idea of this machine learning or unsupervised means machine learning methods, whether it's transferable or not. And for that, we have chosen a different set of systems. And all this was reported for, like, the glass transition temperature was reported for these acrylic polymer mills. So this is a simulation done in our group. So what people found that if we increase the side chain length of the polymer, then the glass transition temperature decreases because the side chains can fluctuate more. And this is people found in other experiments also. This is done in all atom simulation. So what we thought, why don't we use the same data? Because what we care about all the distances. So for all atom simulation, we can use the same data. And as you can see, for this system, the fitting really depends on how much data, how many points you choose. And for the coarse grain system, this change was pretty much clean, but it's not always true, as I can tell you from this point, like from this plot. Like in many cases, the transition happening in a much gradual rate, and that's why these are called like soft transition. And how to pinpoint the precise determination of glass transition temperature for this kind of material is an important topic of current research, and people are trying to come up with different descriptor based on different quantities, especially for polymer mills and small molecules, to reduce the error of the fitting and define a precise value of the glass transition temperature where this fitting is not clean. So this was our idea. We use the same methodology, take one chain and calculate some distances, use dimensionality reduction method followed by a clustering, and see whether this separation is working or not. And we found that, interestingly, for our method works well for this system, and when we increase the side chain length, then the glass transition temperature decreases, and the trend is actually correct, whatever people found in earlier. And we can also treat the data. So we have two ways of treating the data. One was like combining the whole data, and the other part was like treating every temperature separately. So if we do that also, we can come up with first eigenvalue or participation ratio, which shows a non-monotonic behavior around TG. So we applied this method, and you can see this first eigenvalue or participation ratio shows a similar trend for this. When we increase the side chain, the TG decreases. But the interesting thing is that this is not based on some macroscopic property like volume or density. It's rather some microscopic detail in the system, which we are connecting to a material property like a glass transition temperature. And also we can get rid of like choosing how many points to take during the fitting. So there are always human bias while fitting the data. We can get rid of that also. So this is the overall idea. We have, like, I came to the end of my talk. So we develop a framework which can determine glass transition temperature for different polymeric mills and other system also. With that, I would like to acknowledge my mentors, Dr. Alexander Kukharenko and Professor Kurt Kramer. And I would also like to thank Dr. Xiaoping Xu and Dr. Ayşenur İskirin for sharing the trajectories with me, simulation data with me. So Xiaoping did the simulation for coarse grain system, and Ayşenur did the simulation for all atom system. And yeah, all the theory group like in our institute. And thank you for your attention.
Thank you very much, Atreya. Questions? Yes, I already see one question. So, Johnny, if you would like to ask the question, please unmute your mic. Can you speak, Johnny? However, I can read the question. I would like to know how much of the total variance is accounted by the first two principal components.
Yeah, so the first two principal component almost like counts for 50% of the data. I think I should have a plot in my supporting slide to show that. Where is that? Yeah, it should be somewhere. So it is like 20, so 25% and 10%, like 40%. And then there is a gap after 4. Yeah.
How much?
Okay.
Is little.
Other questions?
But
If this is not the case, we thank you again, Atreye, for your presentation. I also would like to thank Alessandro and Laura for delivering these lectures. And now there is more time for discussion during the poster session.